Welcome back. We're in section 4.2 now. We're going to begin a new topic here, although this is very much related to the scatter plots and correlations we discussed in section 4.1. The topic here is least squares regression. This turns out to be an enormously useful and widely used tool. It's used in just about every area of science, engineering, business, just about any area you could name. It's a very widely used tool that you want to be familiar with. Now, in this video, we'll address Objective 1, finding what's called the least squares regression line. Sometimes you might hear it referred to as the line of best fit, and we'll use the line to make predictions. And eventually, we'll define what we mean by the term least squares. Now, there are certain prerequisite math skills that you're going to need, and that you've certainly seen before, but we're going to want to take a few minutes to just remind ourselves of a few of these things. So thinking back to geometry and algebra class, let's think about how many points we need to determine a line in an XY coordinate space. The answer is 2. And let's recall the equation of a straight line in XY space. We can write it as y equals mx plus b. Recall what the m stands for. That's the slope. And what does the b stand for? That's the y-intercept. So, to get us back into the swing of thinking about this sort of thing, let's do a few practice exercises. First, let's determine the equation of the line with a slope of 3 and a y-intercept of -9. Well, we think about our slope-intercept form of the equation of a straight line, y equals mx plus b, and simply fill in the spots for m and b. That'll give us y equals 3x minus 9. Our next problem is to determine the equation of the line with a slope of 1/2 or 0.5 and containing the point 0, 5. Now there are a couple of ways to approach this, but let's think about our point slope form of the equation of a straight line. Y minus y1 equals m times x minus x1. Now m is the slope, and x1 and y1 are the coordinates for one particular point on the line. Well, we have the slope is 0.5. We have one particular point where x equals 0, y equals 5. So we can substitute those values into the equation. That's going to give us y minus 5 equals 0.5 times x minus 0. From here we're going to have y minus 5 equals 0.5x. And if we move the 5 to the other side, we'll have y equals 0.5x plus 5. Now, we could have skipped most of this by recognizing that the point 0, 5 is the y-intercept, and so we could have simply written down y equals 0.5x plus 5 without going through all the steps in this calculation. So let's look at one more problem. Let's determine the equation of the line with a slope of -2 and containing the point -4, 10. Well, again, let's remember the point slope form of the equation of a straight line. Y minus y1 equals m times x minus x1. Now let's substitute the slope of -2 in for m, and we'll substitute -4 for x1 We'll substitute 10 for y1. That's going to give us y minus 10 equals minus 2 times x minus negative 4. We can rewrite this as y minus 10 equals minus 2 times x plus 4. This simplifies to y minus 10 equals minus 2x minus 8. And finally, we'll move the 10 to the other side. Gives us y equals minus 2x plus 2. So now, let's look at some sample data. Here are 6 data points. For each of these data points, I have an x and a y value. Of course, we can plot this data in a scatter plot, and we see that there's a general linear trend to the data. As x increases, y tends to decrease in a fairly linear manner. So now, here comes the new part. We could imagine modeling this data with a straight line. In other words, we can imagine overlaying a straight line on this scatter plot with the idea that the line represents the underlying linear relationship between x and y. But now a natural question is, what's the best straight line? Because here's one straight line, and here's another. And here's another straight line. So what we need is some criteria for thinking about which straight line is the best. Now, here's one idea. Let's select 2 points out of our 6. Say the points 2, 5.7, and 6, 1.9. And let's draw a straight line through these 2 points. Now let's use this line for prediction. Suppose I want to predict the value of y when x equals 3. That is, we want to know the value of y at this point. Now this line is representing the underlying linear relationship in our data, so if I want to predict the value of y when x equals 3, what I want to be able to do is pick off the value of y when x equals 3 on the line. Well, in order to do that, we need the equation of the line. So we're going to want the equation of this line in y equals mx plus b form. Now to do that, we'll first calculate the slope of the line using our 2 points. So remember, we used the points 2, 5.7 and 6, 1.9, and we drew our line through those 2 points. So as a first step, we're going to calculate the slope of that line. Recall that the slope is the change in y over the change in x. So we're going to take 5.7 minus 1.9 over 2 minus 6, and that gives us a slope of minus 0.95. Now we can use our point slope form of the equation of a line, where we can plug in minus 0.95 for the slope m, and we can plug in 2 and 5.7 for the x1 and y1 coordinates of one of our points. This is going to give us an equation of the line that turns out to be minus 0.95x plus 7.6. So now that we have the equation of the line, we can use this equation to predict the value of y when x equals 3. So we take our equation y equals minus 0.95x plus 7.6. We plug in x equals 3, and we get y equals 4.75. So, the point x equals 3, y equals 4.75, that's the point on the line with an x-coordinate of 3, and we interpret y equals 4.75 as our predicted value of y whenever x equals 3. But now you notice that we actually have a point in our data where x equals 3. And the y value for that point is y equals 5.2. So we can now think about how much the predicted value from our model misses the actual observed value for this particular data point. And the difference between the observed value of y and the predicted value of y is called the error or residual. So from our last calculation, we'd say that the residual for the point 3, 5.2, which was actually a point in our data, the residual is the observed y minus the predicted y, which is 5.2 minus 4.75, or 0.45. So the interpretation here is that when we try to use our straight line model to predict the value of y when x equals 3, our model missed the actual observed value of y by 0.45. Now that's okay, because a straight line model is obviously not going to hit all the observed points in our data, since they don't all fall in a straight line. But now this brings up an important idea. We've already shown that there are lots of different lines that can be plotted through these data points. In theory, there are infinitely many straight lines that could be plotted through these points. Every time I have a different slope and a y-intercept, I get a different line. So the question is, what's the best line through these points? Well, to talk about the best line, we have to specify some criterion. In other words, we have to say best by what standard? And the standard criterion that's usually used to answer this question is called the least squares criterion. So the least squares criterion says that we're going to try to find the line through these points that minimizes the sum of the squared errors, or the squared residuals. In other words, for every point in our data, given a line through those points, we can calculate a residual. And the residual, again, represents the amount by which our model, which is the straight line, misses the observed data point. So in a sense, the residual represents the error in our model. So what we're going to do is square each of the residuals and add them up. We sum them up across all of our data points, and that sum represents the total error in our model, how much our model misses the observed data points. But what the least squares criterion says is we're going to find the line through the data that gives us the smallest total error. In other words, we're going to find the line through the data that gives us the smallest sum of the squared residuals. Now in our next video, we'll take a data set and calculate the regression line according to the least squares criterion, and we'll use it for prediction.